Now that we've talked about Newton's first law, we're now ready to move on to Newton's second law. Now, Newton's second law is a lot more useful. It's probably one of the most useful physics equations you'll encounter this semester. But it's also a little more confusing, at least at first glance. It's not something you should be scared of, but you do need to apply a little brain power to understand it fully. And Newton's law, in his own words, runs something along the lines of acceleration is directly proportional to force and inversely proportional to mass. Now that's both a little wordy and a little tricky, so let's try to settle for something a little simpler. Instead, we write it as a single equation, one of the most famous physics equations. F equals ma. Now what does all that mean? F is force. And we really should write F with an arrow over the top. That means force is a vector quantity. And then acceleration is also a vector quantity. M is a scalar. That means M is just a constant. So whatever direction force happens to be pointing in, that means acceleration is going to point in the same direction, multiplied by some constant. So what does that mean for our day-to-day life? What does this F equals ma really imply? Well, what we're actually saying here is force is proportional, acceleration is proportional to force. So let's rearrange this for a second. Let's call it force divided by mass equals acceleration. And this is certainly how Newton saw it. And that's because it's very easy to observe acceleration. It's a little harder to observe, look at mass or force. If you have a rock sitting somewhere, it's pretty easy to see. Is it accelerating left? Is it accelerating right? And if you pick it up, you can test it. You can see its mass. And if you're the one pushing, you can see the force, either left or right. But it's really easy to measure the acceleration. So what he said is, if you apply a force, the acceleration is proportional. That means on our rock, if we apply a force this way, we'll get some acceleration. If our force is twice as long, our acceleration is twice as great. It also means if we change the direction of the force, we'll change the direction of the acceleration. So all of these things are true based on the fact that force and acceleration are equivalent with only a single constant differentiating them. But let's look at this constant for a second. What's the mass doing here? This is saying mass resists acceleration. And that's one of the two fundamental properties of mass. The other one being that it creates gravitational fields. And what we mean by resisting acceleration is if your mass, if you have some mass, it takes a certain amount of force to create a certain amount of acceleration. But if your mass is twice as big, suddenly the rock gets a lot heavier. Now we find that that same force produces only half the acceleration. And if you double that force, you get the original acceleration, even though you're exerting twice as much force. So this should provide a basic understanding of what F equals ma is saying. It's saying that big force leads to big acceleration, and small mass leads to small acceleration. Sorry, to large acceleration. So that means if you're pushing on something and you want to make it accelerate faster, you have two options. You can double your force if you want to make it accelerate twice as fast. Or you can halve the mass. And this is pretty intuitive. If you're pushing a crate full of bricks, what you'll notice is there's two ways to make it go faster. You can get a second guy to help you push. So if you're pushing here, you can recruit a friend who will also help you push. Once again, sorry for the terrible art. Or you can unload some of the bricks. You take the bricks out, and now you have a new, smaller crate of bricks. And now you can easily push that on your own. So you can accelerate it twice as fast. And that's one of those cases where F equals ma is also a very simple equation. You could have come up with it on your own. But it's one of these equations that also evaded physicists for a long, long time. But once Isaac Newton discovered it, it created a new golden age for physics. So this equation can be a little easier to understand once you already know the first law. And now you know it, we're ready to move on to the third law, which can be a little tricky, but it's also very useful for a number of problems.